All right, good morning, everyone. Can everyone hear me? Louder? I'll hold it. All right, can you all hear me now? All right, perfect. Okay, so thank you for joining us today, whether you're in person or watching us online. I'm really excited to have you here for our last speaker presentation of the semester for our NU at Noon Spring 2017 season. So I'm going to introduce our speaker today. Unfortunately, Joe Hunt is on vacation, or else he would be doing it. So Charles Hillman received his doctoral degree from the University of Illinois, where his primary appointment was in the Department of Kinesiology and Community Health. He also held appointments in the Department of Psychology, the Division of Nutritional Sciences, the Neuroscience Program, and the Beckman Institute for Advanced Science and Technology. In 2016, he moved to Northeastern as a professor, where he currently holds appointments in the Department of Psychology and the Department of Health Sciences. He directs the Cognitive and Brain Health Laboratory, which has the mission of understanding the role of health behaviors on brain structure, brain function, cognition, and academic achievement to maximize health and well-being and promote the effective functioning of individuals across the lifespan. Dr. Hillman has published more than 150 refereed journal articles and manuscripts, such as in Nature Reviews Neuroscience, the Journal of Cognitive Neuroscience, and Medicine, Science, and Sports and Exercise. In addition, he has published 10 book chapters and co-edited a text entitled Functional Neuroimaging in Exercise and Sports Sciences. He has served on an Institute of Medicine of the National Academics Committee entitled Educating the Student Body, Taking Physical Activity and Physical Education to School, and is a member of the 2018 Health and Human Services Physical Activity Guidelines for Americans Advisory Committee. Dr. Hillman's work has been funded by the National Institute of Health, IARPA, Abbott Nutrition, Danone Research, and the Nike Foundation. Finally, his work has received media attention, including coverage by CNN, NPR, Good Morning America, ABC World News with Diane Sawyer, Time, and the New York Times. Today, Dr. Hillman will discuss his research program that has investigated the relation of health behaviors and physiological response to cognitive and brain health during pre-adolescent childhood. So please join me in welcoming Dr. Hillman to the front of the room.
Good afternoon. Thank you, Samantha, for the introduction. I figured before I get started, I'd give you just a very, very brief history of me. So I spent 16 years at the University of Illinois as a professor, where this past year I moved to Northeastern along with my longtime colleague, Art Kramer, who serves as the Vice Provost for Research and Graduate Education at Northeastern. But what's interesting is that I've actually come full circle, because I grew up in Mission Hill, and I'm now located in the new Interdisciplinary Science and Engineering Complex on Columbus Ave, which is a beautiful building. If you haven't seen it, you must see it. It's really architecturally stunning. And while most people look out, I hope it's the north side of the building. I'm not very good at my directions, at the Prue and the Hancock and what have you. I actually turn around and look out the windows of my office on the south side, because I have a view of Mission Hill. So it's actually quite nice, and it's nice to be home. And so with that, today I aim to talk about mostly children. So one thing about the work that Art and I do together is that I'm more developmental focused. I study kids more. He's more aging focused. And so we work together, but we have our own personal interests. And so I've grabbed some of the slides from him. So at the very end, I'll talk a bit about aging as well. And so, already off to a rousing start. All right, with that, I'll just give you a bit of an introduction. I don't think it's a surprise to anyone that kids are becoming increasingly more sedentary, and with each passing generation, we find that they're more engaged in sedentary behavior than ever before. By example, if we look at the percentage of children that meet daily physical activity recommendations, which, if you're unaware, recommendations for physical activity amongst kids is 60 minutes or more of moderate to vigorous physical activity on a daily basis. If you look at the percentage of kids who meet those recommendations, you can see that in the 6 to 11-year-old group, they're not doing so well, but they're doing better than everyone else if you get to 12 to 15 and 16 to 19. And so the idea is that kids are becoming not only increasingly sedentary, but they're failing to meet guidelines. And as a function of this, there's an increased prevalence of being overweight and unfit. And if you look at trends in the United States, these are data from 1985 to 2010. And what you can see is over here, the interactive map, you can see that the country has gained mass over time. This is a percentage of individuals who are obese, and of all individuals that are obese. And if you look along the right here, these are snapshots of 2003, 2007, and 2011, and these are just children. And you can see that school-age children are not exempt. They're also becoming increasingly overweight and obese. Now, when we consider the obesity epidemic, and I'm not going to talk a lot about obesity today, it's just by way of introduction, we know some of it has to do with metabolic imbalance. And that is to say that this is a graph, and if you look at the top, these are the things that kids should eat. These are things like whole grains, vegetables, fruits, dairy, seafood, oils, fiber, potassium, vitamin D, and calcium. And these are the goals. And you can see that kids are failing to meet the goals established in the United States for proper dietary health. When we look at the things that they should limit, such as saturated fats and sugars, refined grains, sodium, saturated fat, all the good stuff, right? All the donuts you guys are eating here today. And actually, I think I read somewhere yesterday, I can't remember if it was the paper or if it was on Twitter, I guess there's more donut shops per capita in Boston than anywhere else in the world. So we like our donuts. So anyway, if you see what we should be limiting, you can see that in some cases we're grossly over the limits, 280%, 200%, 149, 110%. And so we're taking in too many calories, and the composition of those calories aren't healthful. And so if we switch and we don't talk about calories in, but we talk about calories out in this metabolic imbalance, what we find is that sedentary children oftentimes become sedentary adults. When we're kids, we have the advantages, in some cases, of physical education. Certainly we get physical activity breaks in our day. And this is traditionally, until this generation, this has been part of U.S. education. And so kids learn to be physically active, and they have time to be physically active. As you know, as you become adults and go through school and have children of your own and mortgage worries and insurance worries and all those sorts of things, it's harder to find time to be physically active. And so we rely on the behaviors we learn as kids. And so this is trends of physical inactivity in the United States. And you can see a large percentage of the population, particularly in this region, almost a third of the population is completely inactive. And reports have identified inactivity as the 4th leading risk factor of non-communicable diseases. And so this is something that can be corrected quite easily. And this one doesn't come out very well. I guess I was told the bulb is on the fritz. But just to tell you briefly, if we consider the implications for our military preparedness, the U.S. Department of Defense has estimated that as many as a third of military-age youth are ineligible for service due to their weight. Nearly 27% of 17 to 24-year-olds are too overweight to serve, and the U.S. military has spent $1 billion on weight management in their recruits. And this has actually led to 2 publications by U.S. military called Too Fat to Fight and Too Fat to Fight Too. And so there are implications. To continue along with this happy story, recent estimates have indicated that this generation of kids, these younger generations of children right now, will live less healthy and have shorter lifespans than their parents, marking the first time in U.S. history. And obesity and inactivity is part of that reason. Now, I'm going to give away the punchline right here and tell you that a growing number of school districts are eliminating physical activity opportunities during the school day in order to make more time for formal classroom education. And this is a problem, right? So where kids were once receiving physical activity, they no longer are. Now, the punchline to this is that there is no evidence in the literature And I've just completed to date the largest systematic review with a bunch of my colleagues on this field. And as mentioned before, I currently serve the Physical Activity Guidelines Committee. And I can tell you that having reviewed this entire literature, there's no evidence to suggest that time spent being physically active detracts from academic achievement. That is to say that there are two outcomes that have been found in the literature. Either physical activity behaviors are positively related to academic outcomes, which is great, or they're unrelated. If they're unrelated, that's also good, because what it means is that we have a more physically active, more healthful individual at no cost to academic attainment. Now, work from my own laboratory supports these data, or this area. These are data from Illinois. Most of the data I'm going to show you today is still from the University of Illinois. Sorry. And what we're looking at here on the x-axis is the number of times they passed different fitness components of the fitness gram. When I was a kid, it was the President's Physical Fitness Test or President's Physical Fitness Challenge. That's been overtaken by the fitness gram. And the number of times they fell within the healthy fitness zone on these tests was correlated with their performance on the Illinois Standardized Achievement Test of Math and Reading, which goes from 200 to 400. And so there's this nice relationship between their ability to pass fitness tests and their ability to achieve in school. When we break it down and we look at the various components of physical fitness, what we found was two that were related to academic performance. The first is pacer. Pacer is a shuttle run. You run between, I believe it's 10 meters between two lines, and you have to run over and back, and you have to cross the line within a given period of time. That time gets shorter and shorter and shorter. So quite simply, this is the number of laps run. And more laps run is related to better academic achievement. When we looked at muscle fitness, strength and flexibility, we saw no relationship in these children. And when we looked at body mass index, we found that with increases in body mass index, we saw decreases in academic performance. So it appears that the cardiorespiratory component, the aerobic component, and the body mass components were related to academic performance. Now, most of the work in my laboratory focuses on brain, as well as underlying aspects of cognition that are involved in everyday life, such as academic performance. And so really what we're interested in is the concept of plasticity. This is our ability to adapt to change. In this case, we're talking about changing in brain, and so we're talking about the ability to form rapid modifications of existing connections within the brain. And so while all this says here is that while we have to give credence to genetics, and certainly genetics provides the backdrop for growth and maturation, I'm going to argue today that it's experience that shapes much of brain's plasticity. And I had a colleague who passed several years ago at the University of Illinois named Bill Greeno, and he talked about experience-dependent and experience-expectant influences. Experience-expectant influences are those that the species expects. And so, for instance, in order for the visual system to develop or mature properly in the first year of life, you need exposure to light and gradients of light. You can't be reared in darkness and expect the visual system to develop appropriately. Experience-dependent influences, these are influences that are idiosyncratic to an individual. And so these are the experiences that we seek out in life that we maybe practice within that have some implications and allow us to shape brain. And so here's some examples of idiosyncratic experiences that have been demonstrated in the literature to have an effect on brain and cognition. For instance, vocation. There's great work of London taxi drivers that shows that those taxi drivers have greater volume and greater function of the hippocampus, an area of brain that's involved in memory. And you can imagine as a taxi driver, when they have to get from A to B, that they're going to need to remember how to go. Now, they compared these guys with London bus drivers. They drive the same route every day. And they found that driving a taxi led to better size, greater size, and greater function of that particular piece of tissue in the brain. Music, the literature of music suggests that it's better to be the conductor than it is to be in the orchestra. And it's better to be in the orchestra than to be a knowledgeable listener. There's work on sport from some of my early work as a doctoral student at the University of Maryland with my advisor, Brad Hatfield, that shows that elite marksmen have differential patterns of brain function compared to less elite marksmen. And certainly there's work around the new millennia on juggling, showing changes in brain structure and function that dissipated when they stopped juggling. And so with that, let me first talk about brain structure. All the work I'm going to talk about today until we get to adults is in 9 and 10-year-old children. We account for all kinds of factors like age and IQ and pubertal timing and sex and grades and all that kind of stuff. I'm happy to answer questions on that, but I'm going to fly through just talking about mostly 9 and 10-year-old kids. This work on brain structure is all cross-sectional at the moment. We just finished a randomized controlled trial of 250 kids, and so we'll have longitudinal data in the coming months. And so when we look at brain structure, we're able to identify differences in We're able to identify differences in high and low fit kids when we look at both gray matter and white matter. So over here on the left is differences in gray matter. And what we find is that areas like the superior frontal cortex, areas of the brain involved in higher order cognitive function, tend to be different in high fit compared to low fit. In this case, we find that there's thinning involved, which makes sense because as individuals mature throughout the course of development, they grow an overabundance of neurons that then deplete out as they're sculpted as they learn new behaviors and learn what's necessary and what's not. And then over here, we see differences in white matter between high fit and low fit individuals. High fit tend to have greater integrity of white matter structures, which is important for transmission of information between the different areas of the brain. Now, other imaging studies in our lab have tried to compare fitness with differences in brain structure with differences in cognition. And so one area in particular that we're interested in is the hippocampus. The hippocampus is involved in memory. This is a subcortical structure. It's involved in aspects of learning and memory. And as I mentioned before with the London taxi drivers, it allows you to figure out where you were and what you were doing and how you got there. Now, it's important for other aspects of the day. For instance, here's a scene of people having dinner. And in order to remember that scene, you have to put it back together. When you're if you think back to your last dinner with another couple or several people, you might think about who sat on your right, who sat on your left, who ate what, who said what, who drank what, and so forth. And by remembering all of those, it allows you to put together the scene and remember that time. And so we're interested in the hippocampus for that reason. And what we find is that high fit very clearly have greater hippocampal volume, greater size in the hippocampus bilaterally, both sides of the hippocampus, compared to lower fit kids. Now, importantly, when we look at their behavior, we give them 2 memory tests. The first one is hippocampal independent. That is to say that these memories are formed outside the hippocampus. And the second one is hippocampal dependent. That is to say that the hippocampus is necessary in order to form this type of memory. We find that higher fit only outperform lower fit on memory tasks requiring the hippocampus. So we're not seeing a generalized relationship between fitness and brain. And cognition. We're seeing a selective relationship, such that it's important for certain aspects of memory, not all aspects of memory. Secondly, we're interested in a type of cognition called executive control. Most of my work is in executive control. And executive control is a type of cognition mediated by prefrontal cortex up front here and an associated network. And these are the types of cognition that are important for everyday life. You use executive control when solving unique situations, when having to remember items and their placement, when having to perform novel tasks. Use executive control in order to regulate your behaviors, right? To not, lash out in the middle of my talk and tell me that this is all foolish and I should sit down, right? You can save that till the end because we have the ability to inhibit ourselves, right? And it's very important for school. And so executive control is generally parsed into 3 different areas. Inhibition, which is our ability to ignore distractions, stay focused, our ability to withhold inappropriate responses in favor of correct responses. Working memory, holding information in our mind and manipulating it. An example might be carrying the remainder during a long division problem, or remembering a passage that you then have to answer questions about. And cognitive flexibility. This is something we all believe we do very well. This is oftentimes called multitasking, but in essence, we don't do this very well, in the sense that we can perform one task better than we can perform two tasks. And so what we're talking about here is the ability to perform one task, put that task on hold, execute a second task, put that task on hold, and go back and forth. This oftentimes has led to problems, for instance, during texting and driving and those sorts of things. And so here's data of the basal ganglia. Again, this is another subcortical structure, and these are just slices of the brain where you can see the different areas lit up. And we compared high and low fit kids, and again what we found was that higher fit had greater volume in areas of the caudae, putamen, and pallidus, areas of the brain that are involved in executive control. But when we looked at the nucleus accumbens, this is also part of the basal ganglia, but it's not involved in executive control. It's involved in affect or emotion and reward. And what we find is that there's no relationship there. So again, we see selectivity in the relationship between fitness and brain structure. Now, most of what I'm going to talk about for the remainder is brain function until we get to adults again. And brain function is interesting because it allows us to actually look at changes in how the brain works with performance, and whether aspects of health behaviors influence brain function. And so with that, I'm going to talk about what I've been doing with the last 10 years of my life. For the last 10 years, I've been involved. I've directed an NIH award that we termed FITKids, Fitness Improves Thinking in Kids. And this is an after-school program that I created. And the goal was to get kids moving for over 60 minutes a day. Remember, I talked about the physical activity guidelines for children. And so these are data from the first 5 years. This was the first grant. The second 5 years just ended just about 2 weeks ago. And so we'll have some more measures soon. But kids came, in the summertime, they came to our lab. We tested them, and I'll talk about that in a bit. And then we randomized them either to an after-school program or to a waitlist control group. If they got the waitlist, they were able to join the after-school program 1 year later untested. Those that were in the after-school program as part of the testing, they came every day after school on 150 of the 170 school days. They did half days. There's no program. We ended up collecting 221 children, fairly evenly split. And in the intervention, we found that over the course of the year, they averaged greater than 70 minutes of moderate to vigorous physical activity intermittently delivered over the course of a 2-hour period. And that resulted in just shy of about 5,000 steps during that time. There's efficacy in our intervention, as I show here. You can pick either one, but basically what I show is that they increased their cardiorespiratory fitness, their aerobic fitness, over the course of that 9-month period in the intervention group compared to the waitlist control group. So they improved by about 6% as opposed to about 1%. And when we look at their behavior on tasks of executive control, over here on the left is our inhibition task, our ability to ignore distractions, stay focused. We find that that they improve by just shy of 8% following intervention, physical activity intervention. Compared to waitlist control, which is typical development, we find that they improve by a little less than 4%. So almost a 2-fold increase in performance. When we look at multitasking, or their ability to switch perspectives or switch task sets, perform 2 tasks at once, we find they improve by about 10%, or they improve by less than 6% in the waitlist control group. So we're seeing increases in cognitive performance beyond that of typical development. When we look at brain function, we see a change in brain function here and here, but only in the intervention group. And we only see that when the task is most difficult, when it requires the greatest amount of executive control. And these are the intervention, this change for intervention with a limited change for waitlist control. And this change in brain function is thought to be related to the allocation of attention. And so they're allocating more attention towards those stimuli that we're delivering to measure executive control. And so what we showed was that those in the intervention accrued more fitness, performed better, and had greater brain function to support their performance. And now, when we looked at just the kids in the intervention, we forget about those in the waitlist control group. What we find is that those who attend the after-school program the most show the greatest change in brain and the greatest change in behavior. And so teachers say that students need to be present to learn, and we find something similar, that children need to be present in the after-school program in order to derive the physically active benefits that then have an effect on brain and cognition. And so we know that there's an epidemic of sedentary behavior in the United States. We know that people don't like to be physically active. This is evidenced by reports of, as I demonstrated, of kids of less than 20% of children being active at appropriate levels. And so I understand there's time constraints, there's safety constraints, there's monetary constraints. And so the question is, so one question we've been asking a lot is whether or not a single bout of exercise can promote a temporary change in brain. We know that it won't promote lasting change because that's something we have to practice and do on a daily basis in order to create that that shift in brain that I talked about before, the ability to shape brain with behavior. But maybe a single bout of exercise has efficacy in promoting a temporary change. And so with that, we looked at children, we brought them into the lab on a couple occasions, and on one occasion they walked on a treadmill for 20 minutes at a very moderate pace. This is an intensity and a duration that every child could do. We never, they didn't sweat, they didn't complain. It was easy for them. They enjoyed it because they were on a treadmill. Many of them for the first time. And we compared that with 20 minutes of seated rest, where they were given the option to read from a selection of books that we had available. And what we found was that following their exercise condition, we showed an increase in that brain function associated with attention, as you can see here. And this is the rest condition. And again, this is the condition that requires the greatest amount of executive control. In conditions that require lesser amounts of executive control, there is an increase, but it's not as great. And so again, we're seeing not just that in this case, a single bout of exercise promotes an increase in attentional resource allocation in the brain, but we're seeing that's selectively related to tasks requiring greater amounts of executive control. We replicated this. We've replicated it now 4 or 5 times. We've replicated it in children with ADHD. Again, here they are post-exercise. In the ADHD kids, we gave them reading material because they had a hard time sitting still and doing nothing. And when we look at their performance, here typically developing kids and here ADHD kids, we see that following that bout of exercise, they're more accurate on that task of inhibition that we give them, as you can see here and here. And there's no difference in the speed in which they perform the task, which is very important. They're more accurate at no cost to speed. And importantly, when we give them then an academic achievement test in the laboratory that's standardized and used widely, we find that there's improvements following the bout of exercise for reading and arithmetic, but not spelling. And according to the manufacturer of this academic achievement test, this is a full grade level increase in performance. And so through the course of multiple experiments, we've learned that this effect lasts for approximately 1 hour. Now, we're not sure when it begins. We know it doesn't begin immediately after. It appears to begin somewhere around 10 to 15 minutes after. And so following that bout of exercise, it appears they need a little lull, and then they derive a benefit of being physically active for approximately 45 minutes after that. Now, one of the things we do in the laboratory is we give them these tasks and we speculate on how this performs in everyday life. But the problem is that it's not everyday life. It's a laboratory, it's highly controlled, and so we've gone into schools and we've tried to do work there, and we've published some of that work as well. But one of the things we've tried to do is to get closer to everyday life for a child by giving them cognitive tasks that may actually occur in the school setting. And here's an example. We had children come to the laboratory. These are cross-sectional data, so they're either very high fit or very low fit, and we're replicating this in the MR in the MRI soon. Sorry, it'll be finished soon. Anyway, they come into the lab and they learned a map. They received 2 different maps. These are fictitious maps. There's 20 regions, and in 10 of the regions on the left, the name of the region appears. In this case, it's Taft. The individual taps it to say that they've seen it, and it goes away, and the next one comes up. And they receive these 10 names in 6 blocks. And so they see 10 names, they get a rest, they see 10 names, they get a rest, so forth, 6 times. In the other case, and we call this the study-only condition, because it appears, they study it, they tap that they've seen it, and they go to the next one. In the other condition, we give them a test study condition, where the name appears on the right, they then tap the region where they believe it is, so they're testing themselves, and then they see whether or not they got it right. And so this is actually a strategy. We're giving them a strategy in which to learn. Many of you might recall back to when you studied, you oftentimes might have, instead of just tried to memorize each thing, you might have tested yourself along the way and then checked to see if you did it correctly, and you do it again and again and again. And so this is a learning strategy over here on the right. And so importantly, on the day they learned this information, the day they encoded it in their memories, you can see that in that test study condition, by the 6th block, everyone was pretty much the same. They're all about 85, 90%. Whether they're high fit or low fit, they performed equally well. So then we had them all come back 24 hours later. If the learning day was at 3 p.m. on Tuesday, they had to come back on Wednesday at 3 p.m. So they all were, it was a 24-hour period. And we gave them a recall test. We asked them to remember whether or not they could recall the regions. And so they did this in 2 conditions, either a free recall condition, where they clicked in each one and they typed in the name of the different regions, or a cued one, which is easier because we gave them the names of the regions below, and they just had to write them in or type them in. And what we found was that higher fit outperformed lower fit on recall, having to remember that information, but only so in the study-only condition. That is to say that when we left them to their own devices and they had to remember this information, high fit outperformed low fit. When we gave them a strategy as to how to remember this information, everyone performed equally well. So not only is this a good metric or a good example of differences in fitness, but it's also a good example of different learning strategies. And we broke it down in the 2x2 fashion of the 2 types of encoding, 2 types of learning, and 2 types of remembering. We actually find that the hardest condition, the study-only free recall, where they had to remember it all from their minds, that was the largest difference. The difference went away in the cued recall, it went away in the test study cued recall, and there was a small effect in the test study free recall. So test study had some relationship, but clearly study only was where we saw the greatest effects. Suggesting that that you can look at this a couple ways. You can look at it in the way of that higher fit outperform lower fit, or you can look at it as from the direction of lower fit individuals are able to have similar performance to higher fit individuals when given the proper strategy to learn. And so with that, I'm just going to spend a couple minutes finishing up today talking about aging. I gathered that there would be a number of people in here older than I am, and I figured that it would be best to show you some of the data that this is not just good for kids, right? These data, they're not there across the lifespan because there's a paucity of data in certain periods of time. School-age children, we see the effects anywhere from, say, kids as young as 6 to about as old as 14, and then we get some 17, 18-year-olds. So we're missing data under the age of 5, under school age. We know that young adults, college age, convenience samples for those of us who study on college campuses, we know some data there. But once people turn about 30, we don't really know much about the lifespan with regard to physical activity and cognition until really about 55, and really more 60 to about 80. And so we do see it at the various extremes of the lifespan, but we don't see it. We don't know much about middle age. And so to start, let me just say that as probably many of you can tell me, cognition across the lifespan is variable. There's this maturation period, there's a period of stability, and then there's a period of decay. Now, different types of cognition decay at different rates. I've been talking a lot about executive control, and I'm interested in executive control because it's mediated by prefrontal cortex. Prefrontal cortex is the last region of your brain to develop. It takes till about 20 or 21 years old, which means that for those of us who see 16-year-olds driving on the streets, it's a little scary. That prefrontal cortex isn't working very well. But unfortunately, by the time we hit about 30, prefrontal cortex is already beginning to decay. And so you really only have about 10 years of optimal prefrontal cortex function. Sorry to inform you of that, but if it makes you feel any better, I'm in the same boat, right? And so if you look here, this is age, and this is performance on various tasks. And you can see there's a natural curve that develops over time of some increase in performance followed by decrease. Now, what's interesting is that when we look at different brain regions, here we're looking at prefrontal cortex, dorsolateral prefrontal cortex, and over here we're looking at hippocampus, the two areas I talked about before. And what's interesting is that it's not a homogeneous decline over time. As you see, again, here we're looking at age from 10 to 90. And if you look out here, somewhere in the 60s, we see that we have this individual up here and this individual down here. They're quite different from each other. There's a lot of variability in aging. The individual on the top here that I've circled, sorry, the one thing about my aging is that I've become more colorblind over time, so I have to really stare at this dot. The one thing about this individual is that they have brain function, prefrontal cortex, similar to that of someone in their 20s. So they've actually aged quite well. This individual over here, not so much, right? They are not doing very well in terms of prefrontal function. Same thing can be said for hippocampus. There's differences. And so there's lots of variability in aging. Now, when we look at the hippocampus and we look at volume, this is cross-sectional data. And you can see a pretty nice relationship. It's actually I think a rather stunning relationship between cardiorespiratory fitness and volume of the hippocampus, size of that hippocampus. With increases in volume, we see increases, with increases in volume, we see increases in cardiorespiratory fitness, and vice versa. It's a relationship, right? It's not, at this point, I'm not showing you data to suggest that it's causal, right? Those that are more active or more fit, appear to have larger hippocampi. And when we look at a randomized controlled trial where individuals were randomized either to a walking intervention, a cardiorespiratory aerobic intervention, what we find is differences in brain structure over time. For those that are randomized to a stretching and flexibility intervention, which is our control intervention, what we find is that despite benefits to the body, that is, increases in musculature, both in terms of strength and flexibility, we don't see benefits in brain. And so you can see here, these are data from the hippocampus, left and right hippocampus, and so you can focus on either one. It's the same effect. But you can see at baseline, those in the stretching condition and those in the aerobic condition are no different. 6 months in, we begin to see differences. And 1 year later, we see strong differences. And these differences in hippocampus are the equivalent, this increase in volume is equivalent to about 2 years. And so they're generating about a 2-year increase in the volume of hippocampus. It's like rolling the clock back 2 years from a walking intervention that was delivered 3 times a week for approximately 1 hour at a moderate pace. When we look at caudate nucleus, that's the part of the basal ganglia that I talked about before, and we look at the thalamus, we don't find any differences. So again, these effects appear to be selective. They're specific to areas of the brain involved in higher order aspects of cognition, such as executive control or memory and learning. And when we look at change in hippocampus, and again, this is left hippocampus and this is right hippocampus, so you can look at either one. We look at change in fitness over 1 year and change in hippocampal volume over 1 year. You can see that those with the greatest changes in fitness show the greatest changes in hippocampus, and those with the greatest decreases in fitness over that time show the greatest shrinkage in hippocampus. And so it works both directions. And so with that, I want to tell you a little bit about what we're doing now. As I mentioned, I'm in the new ISEC building, Interdisciplinary Science Engineering Complex. And myself, along with Art Kramer, a professor at the University of Pittsburgh named Kirk Erickson, who are actively hoping will come join us here one day at Northeastern. So send him an email and tell me you should come to Northeastern. I'm trying. As well as a group at University of Kansas Medical Center. We just received a year ago a $23 million grant from the NIH to study dose-response relationships of physical activity on brain and cognition in older adults. And we're looking at 65 to 80-year-old individuals, and we're collecting a whole host of measures from blood to look at genetics and genotyping, to measures of brain structure, brain function, to measures of cognition, to measures of body composition, aerobic fitness, and so forth. It's a big study. And they're going to get randomized for this 1 year intervention to 1 of 3 groups. Either 150 minutes of stretching. This is our control group, stretching and flexibility. But again, there are health benefits to that. To 150 minutes of moderate intensity walking, which is federal government's guidelines for older individuals. They should receive about 150 minutes of exercise, of walking exercise per week, or it doesn't have to be walking, but 150 minutes of moderate to vigorous physical activity per week, about 30 minutes a day, most days of the week, or 225 minutes of moderate intensity walking. That is to say, what does the dose-response relationship look like if we increase that amount of activity to about 45 minutes most days of the week? And so for the next 5 years, we'll be conducting this intervention out of ISEC, along with Pittsburgh and Kansas, with the goal of achieving about 639 participants in our phase 3 randomized controlled trial. And so with that, I'm going to conclude today. Fitness is related to differences in brain structure and function. Hopefully, I've made that argument effectively today, that there are differences that are achieved by being aerobically fit and physically active. Fitness has been linked to changes in cognition, and these changes appear to be disproportionately or selectively greater for tasks that require executive control, prefrontally mediated function, or hippocampal dependent memory and learning. And so when it comes to children, I would certainly argue that time spent engaged in physical activity doesn't detract from academic performance, and in fact may help it. I briefly touched on that single bouts of exercise have temporary benefits to brain function and cognition and achievement. And so it's possible that, and some schools have already begun to do this, to strategically implement physical activity bouts in the classroom and during the school day in order to promote better performance during academic classes and academic achievement tests. And so schools are well placed to improve children's health behaviors. We know this. This is why we have classes in health and physical education and whatnot. But what's missing is an understanding of academic achievement and cognitive health. And these are areas that schools can certainly do better at improving their understanding and delivery of that message to children. And so early school-based intervention to promote health behaviors is crucial towards lifespan health and effective functioning of brain and cognition. And we know that this is true across the lifespan. And so the effects of physical activity on brain structure and function are especially pronounced during the later stages of the lifespan, as I just showed you. And it's arguable that these behaviors can not necessarily promote longer life, but certainly may promote healthier living during the later stages of the lifespan. And so if you gain nothing else from my talk today, I'll leave you with a cartoon by the New Yorker that says, "I've been working out for 6 months, but all of my gains have been in cognitive function." And with that, I'd just like to acknowledge those in my lab who do the heavy lifting. These are my collaborators and my students and my postdocs, as well as my funding agencies. So thank you. Yes, sir.
I just want to make a comment. I'd like to congratulate you for your professional attire and for wearing a necktie. I'm from the necktie generation.
Thank you. I was taught well by my mother. Okay, so the question was, do I have any plans to look at the relationship with strength training, the relationship to running, and as well as what might be the upper limit for the benefits derived. And so why don't I start there for the upper limit. Lots of people are interested in this dose-response relationship. And what that, to them, what that means is that it's a linear effect, right? A little bit more gets a little bit more, a little bit more exercise, maybe a little bit better cognition. I don't believe that. If you look through the literature and you look through my own data, I believe it's a threshold effect. So there's some threshold that has to be achieved in order to derive a benefit. And then there's some threshold that once you achieve it, the benefit appears to flatten out. And so I don't believe that there's a more is better. But having said that, there are people who are, who will run 100 miles a week. These are our sort of super exercisers, and Art Kramer actually has a very small sample of people who are super agers, right? They're pushing 100 and they're cognitively as intact as ever before, and many of them are highly active. And so I think it's anecdotal at this time, but certainly it's something we talk about, but we don't have a strategy for. Strength training. There is a colleague of mine at the University of British Columbia named Teresa Lou Ambrose. She shows benefits in brain structure and function with strength training. Now, those benefits appear to be muted compared to cardiorespiratory exercise, but she does show that there's a synergy between strength and cardio. And so I would certainly, talking beyond just brain and talking to health, I always say this because I'm sort of forced to, but, always check with your doctor, right? Make sure that's, that you're safe to exercise, which I think is a really funny thing because you know how much doctors know, how much they learn about exercise in medical school? Yeah, zero, right? So, how many times have doctors told me I'll never play hockey again, I'll never bench press again, I should never get on my mountain bike again, right? So anyway, assuming you're healthy and can exercise, if you look at those guidelines produced by the U.S. government, the federal guidelines for physical activity in Americans, everyone stops at the number of minutes per week they should be physically active. But actually, if you keep reading, there are also recommendations for strength and flexibility and bone loading and all those sorts of things. And especially for older women, right? Bone loading exercises such as strength are important, right? And so there are healthful benefits to both brain and body. And then the last one, running. Actually, some of our older adults do run. I didn't get too much into the details of it, but the idea is that we create an individual prescription for every individual. And so what that means is that when you come to the laboratory, we give you a maximal exercise test. This is a really fun test. This is where we exercise you on a treadmill to absolute maximum capacity. And to make it more pleasant, we put a face mask on you, and we pinch off your nose, so you got to breathe in and out of your mouth. And your throat gets really dry. It's really pleasant. But what we do is we get your absolute maximum capacity from that. And from that, we're able to get your maximal heart rate under maximal stress. And then we dial it back and say, okay, we want you to exercise at 40% for the first week, 45%, 50%. We want to get you up to about 65% for then the rest, basically the last 9 months of the intervention. Some people come in more fit than others, so their 65% is actually a run. Some people come in less fit, and so when they get to 65%, they're mostly walking at that point. And this is also true of children, right? The easiest thing in the world to do is to get a morbidly obese child to 65%. That's basically a moderate walk. And so it's individual prescription, so some of our guys do run. And when our cross-sectional work is at higher levels of fitness, and they do run at that case. Quite frankly, I don't care whether you get there by speed or by incline. It's all about just getting there. During the intervention itself, it's a walking intervention, so they walk a track. They wear a chest strap, so we'll have our guys walk right up alongside of them with the watch on, and they'll be able to capture their heart rate and write it down. We give them accelerometers so we can measure the number of steps, right? I mean, the smart technology is incredible. But my mom taught me to wear an old school wristwatch as well. So they have all the technology with them, and we find that that's motivating as well. They'll come up to me and say, like, hey, I was able to get 4,500 steps today instead of 3,500 steps a week ago. And so that's where you see the increase from walk to run. Yeah, thank you. Yes.
Anecdotal, and it's my own lived experience. But in college, I competed in 3 sports. After I rested, 9, 0, it's a lot easier.
Yeah, I mean, I think that's true, and that's a big part of the impetus for our work on acute bouts of exercise. A lot of people report that following a bout of exercise, they feel emotionally more healthy, they have less anxiety, they're happier, they find that they're able to attend better after some period of rest, and so actually, one of the things that we do very frequently in our lab is that especially me, when I write all day, I'll take breaks where I'll just, get out of the office and go for a 10, 15, 20-minute walk, come back, and I find that actually I'm more productive in that time. And so I think a lot of athletes report this. Yes, sir.
To the young of the old program, general health taken into consideration.
Yeah, that's a very good question. So he asked, is general health taken into consideration when deciding on participants for both our child and our aging studies? Yes. Children's a lot easier because it's basically a health history questionnaire that the parent can address, and a readiness to exercise questionnaire that the parent can address. But we do look at certain things in the child's health. For instance, if they have asthma or something like that, that's considered. Not necessarily excluded. That there's a second step then where we would send them to their doctor and get their doctor's approval and get their medication on hand and that sort of thing. With aging, yeah, there's a lot more involved, unfortunately. So step number 1, you contact us and you say you want to be in the study. My research coordinator is going to ask you a bunch of questions on the phone. It's about a 20-minute phone conversation, and then she's going to email you or mail you a pretty, several pages of health history information that you're going to fill out, take to your doctor. Your doctor's going to fill out some of it, and your doctor's going to slap a note on top saying that they believe that you're okay to exercise in how we designed the program. And so quite a few people are not eligible, right? That's probably one of the biggest, I would say, limitations of our work, is that really what we're examining are healthy agers, right? Even if they're unfit or sedentary or overweight, they're still healthy agers. Those who are not healthy enough for everyday exercise as we've designed it, certainly that's a group that really needs to be studied, and there just simply isn't a whole lot of work in that area. There is some work on really ill individuals, though, so individuals, say, with like multiple sclerosis who have a very serious condition as opposed to sort of just lightly, and there's definitely benefits there, and those programs are curtailed to their physical ability. Yeah, thank you. Yes, sir. Yeah. Right. Yeah, and I'm sorry I took those data out. I did not think that was going to be appropriate today. Here I am. I'm always wrong. So the question was, and actually what you're talking about is high intensity interval training, HIIT. And HIIT training is commonly called CrossFit. But I'm not promoting CrossFit because I actually I don't think that it's as good for the body as people think. But HIIT is interesting. High intensity interval training is really designed such that I'd have to go dig it up. But basically, the idea is that you perform short bouts of exercise for about 30 to 45 seconds to a minute, to maybe as long as 2 minutes. And what you're doing is you're exercising at near maximal capacity. So it really is as hard as you can go. And that's followed, that short period of time, let's just say that 1 minute period of time, is then followed by 1 to 2 minutes of very, very light exercise. So, maybe you go from a sprint for 45 seconds to a minute to a walk for a minute to maybe a minute and a half, 2 minutes. And so you get these ups and these downs, these ups and these downs. And because of that, you don't have to do, as some of my data have shown, 20 minutes of walking on a treadmill in order to derive a benefit. We're seeing it as little as 9 minutes. And in that 9-minute period, there's 3 intense bouts followed by 3 light bouts. And we show actually changes in brain function, changes in cognition, and those changes in cognition appear to be larger than moderate walking. What's interesting is that, and the reason I didn't bring it up is because there's a lot of unknown there, is that as I showed you, you see this increase in brain function following moderate walking. You actually see a decrease in brain function following HIIT. But they both, regardless of the direction of change, we see an effect on cognition. And we don't really know what that means. We just got these data published. We just replicated it a couple weeks ago. And in fact, my last student at Illinois, the replication is part of his dissertation that he'll defend in 2 weeks. And this is an encouraging area. I'm a consultant on a grant in Australia. I just got back from Australia, where they're delivering HIIT curriculum to high school kids in class. And so it doesn't have to be a run. They developed this enormous curriculum of HIIT run, HIIT strength, HIIT combat, where they do like karate or some martial arts, I don't know. And HIIT boxing was one of them. So it's these different curriculums to keep these kids entertained, but they're short bouts lasting, I think they're 5 to 8 minutes in each case, and it's with this great up and down. So yeah, that's a really good question. And I gotta say, HIIT is probably one of the largest areas in the field of kinesiology right now, not just with brain, but I mean with body, and looking at differences in its effects on muscle and cell and molecular and whatnot. So yeah. Yes, ma'am. Yeah, that's a good question. That's the mechanism question. Yeah. So that's my mechanism slide. Let me summarize by saying that while we work at the brain and behavioral level, and really when I say brain, we're really working at the systems level, like overall brain imaging. And the thing about imaging is that it shows pretty pictures, right? But it doesn't tell us, why there's an increase in hippocampal volume, right? And even though we have randomized control causal data, we don't know what's going on below that. And in order to get that information, we unfortunately can't do histology work in humans. We offer all the time. No one takes us up on it. So instead, we have to go to animal models. And in animal models, we're able to get that cellular molecular understanding, because what happens is that, you exercise these rodents and then you cut off the head, have a look at their brains and all that. Glad I don't do that work, but I rely on it quite heavily. And when we look at that, we find that there's differences in volume of particular cells, both gray and white matter, as I talked about in humans. But to go beyond that, what we see is that there's differences in some of the neuroprotective molecules, like brain-derived neurotrophin factor. That's a big one. This is a molecule that's involved in long-term potentiation, the formation of new memory in the hippocampus. And what we see is an upregulation of brain-derived neurotrophin factor in rodents following exposure to a running wheel or or forced exercise. We see differences in norepinephrine, serotonin, lactate, all these brain chemicals that are involved in different aspects of mediating the cellular and molecular environment within the brain. We see in some older work that the type of exercise influences what part of the brain or what types of changes we see in the brain. And so, for instance, when you give rats exposure to a running wheel, they develop increases in angiogenesis in the cerebellum. And this is, angiogenesis is an increase in the vasculature of delivery of blood. And blood carries oxygen, so it could be therefore, your oxygen hypothesis that many people have, right? More blood, more oxygen to the brain. But when you give same rodents, when you train them on what we call sort of like rodent Cirque du Soleil, right? They're trained to sort of walk a tightrope, crawl up a ladder, carry a little weight on their tail. You don't see the same thing. You don't see angiogenesis. Instead, you see synaptogenesis. And synaptogenesis is how the neurons talk to one another, and we see that in a different part of the brain, in motor cortex, and so or supplementary motor cortex. And so, depending on the type of exercise, we see different effects. But we do, there is data in molecular cellular systems and behavior, and even more recently, there's been some data on stem cells, and that's come out. And some of my own work is I've paired with a guy who does stem cells, and we look at the obese environment in kids and see how that influences inflammation in the brain. And that inflammation, when it becomes chronic, relates to decay in cognitive function. So there's lots of different areas going on. So, thanks. Any other questions? Yes, ma'am.
If you're looking to sign up subjects, just have a room full of
I appreciate that, and yes, we've thought about. I mentioned that to my research coordinator, and we will get back in touch. Our laboratory right now is a big empty space overlooking a beautiful view of Boston, but empty nonetheless. It's expected to be done by August, and we expect to start recruitment in mid-July. And so I was hoping that I would be able, through Samantha, maybe distribute flyers to people who are interested. And you'll be hearing a lot from us, maybe too much. So, any other questions? Yeah, yes, sir. Mm-hmm. Not spelling. Yeah, so the question is, following that single bout of exercise, I showed some academic achievement data where following the bout of exercise, kids increase their performance on reading and math, but not on spelling, compared to when they sat quietly for 20 minutes. And the question is, why not spelling? We don't know. I didn't design the test. We used a widely manufactured and utilized test. The one anecdotally from my lab techs, they told me that when I had the same question way back, was that that it may not have been a sensitive enough assessment, because spelling is much like math and reading are grade level. Remember, most academic achievement tests are used to assess grade level performance. And what they said was that most kids sort of failed at the same, word or two words. And so that had there maybe been more words around that level of difficulty, it might have segregated people a bit better. But since there's only one or two words, that seemed to be the limit. And so it could be, it could be that aerobic bouts of exercise don't have an effect on our ability to spell. It could also be an instrument failure. So we just don't know. But thanks. Okay, well, thank you for coming today. Thank you for your time.